In this video, I'd like to continue talking about the polar and rectangular forms of complex numbers. And you can see both examples here. This top one is an example of polar form, and the bottom one, an example of rectangular form. And in both of these, we need to convert to the other form. So let's start by reviewing both of those forms in general. We can say we have some complex number z, and this is equal to a plus bi, or I times b, where a is the real part of the number and b is the imaginary part. And when it's written like this, we call this the rectangular form. This is the way you will typically see it if you are just learning about complex numbers. And we've also looked at the polar form of complex numbers, where z is expressed in terms of its absolute value, its magnitude, or its distance from the origin, multiplied by the cosine of theta plus I times by the sine of theta, where theta is the direction of the complex number. It's essentially the angle measured from the positive real number axes. And again, this form right here, where we have its direction and magnitude of the complex number, this is the polar form. And like I mentioned, for each of these example problems, we were given one form and we need to convert it to the other one. So let's start with this complex number in its polar form and convert it to its rectangular form. And the benefit of the polar form is that we can tell right away what its magnitude is, which in this case is 6. It is a distance of 6 away from the origin. And we can figure out what the angle is. In this case, theta is 5 pi over 4, and we're in radians here. And if we want this in degrees, we know 4 pi over 4 would be 180 degrees. Pi over 4 would just add another 45 to that, meaning that in degrees, this is 225 degrees. So if we wanted to look at this graphically, we would see that this complex number is in the third quadrant and would be a distance of 6 away from this origin here. And again, this angle here is 225 degrees, or 5 pi over 4 radians. Now we need this in its rectangular form, and to do so we will essentially just simplify or evaluate this expression. So we can start by distributing the 6 to each of these, and let me actually just make a little bit more room so that we can work this out. And rewriting this problem here, after distributing the 6, we would get 6 multiplied by the cosine of 5 pi over 4 plus I times 6 multiplied by the sine of 5 pi over 4. And we need this answer in exact terms, meaning that we don't want just a decimal approximation. We want to know exactly what the cosine and the sine of this angle actually evaluate to. And for that, we'll need the unit circle. So remember that we have a circle where the radius is 1, and this is a special angle. In fact, it's this point right here. This would be 5 pi over 4, or 225 degrees. And when you create a right triangle around this angle, you have a 45, 45, 90 right triangle, or in radians, pi over 4, and pi over 2 triangle. But this triangle formed here would be the same one formed in the first quadrant, where again, this is a 45-degree angle, or a pi over 4 angle. And if we understand the triangle in the first quadrant, then we can understand the triangle in the third quadrant. Since ultimately with the unit circle, we just need to remember that the xy coordinate of this would be the cosine of the angle for x and the sine of the angle for y. And in the third quadrant, both cosine and sine are negative. So if we can figure out their values in the first quadrant, we essentially will just make them both negative. And since we have this 45, 45, 90 triangle, where actually in our case its hypotenuse is 6 rather than 1, we can figure out what these side lengths are. Since both these angles are equal and this is a 90-degree triangle, With a 45-45-90 triangle, to get the side lengths when you know the hypotenuse, there are two approaches. We could remember the pattern that you essentially just divide by the square root of 2 for each of these. And you get 6 root 2 over 2 or 3 root 2. Or you could call each of these side lengths a variable like x and set up the Pythagorean theorem that x squared plus x squared is 6 squared, and then solve for x and figure out that it is indeed 3 times the square root of 2. So for this pi over 4 angle, or 45 degrees, we know that x and y are both the square root of 2 over 2, or when we scale this by 6, since that's actually what our hypotenuse is, then we would get 3 times the square root of 2. And again, for this triangle down in the third quadrant with this angle of 5 pi over 4, we would get minus root 2 over 2 for both the x and the y values, since they're both negative in this third quadrant here. So these values, before we multiply by 6, would be minus root 2 over 2 for each of these, but when we do multiply by 6, we get minus 3 root 2 minus I multiplied by 3 times by the square root of 2. So this is our complex number expressed in rectangular form. And there are ways to check this, since we know that the magnitude of our complex number is just the square root of its real part squared plus its imaginary part squared, where this would be a and this would be b, so we can check it that way. And we also know the formula for the angle theta, that this is the inverse tangent of the imaginary part divided by the real part, though we need to be careful with the angle since we're down in the third quadrant, and this formula only gives outputs in the first or the fourth quadrants. So for something in the third quadrant, we will have to subtract 180. And for something in the second quadrant, we would then have to add 180 to that just to be able to shift the angle to our correct value. But when we plug both of these in, we will see that this number that we arrived at actually does make sense.